Good evening, everyone. I was hoping that everyone online is able to hear me based on the earlier testing. We are here for an evening seminar supported by IEEE and EPECentre. We are privileged to have Dr. Vosloo here with us, and he is the corporate HV expert from Eskom. He also works with University of Stellenbosch in South Africa. He has authored a book called HV Insulation and a recipient of Claude de Torel Lifetime Award for HV Insulation. He's on not a world tour, but South continent tour in Australia and New Zealand, and he's been giving courses on HV insulation. He's covered Sydney, Brisbane, Auckland, and via Christchurch, he'll be moving on to Wellington. And the subject matter today being optimal selection of HV insulation in polluted environment. I hand over to Dr. Wallace. I just wanted to say we are recording the session, so we will put it on later on, and there are a lot of online participants. So at the end of the session, if you could send me the questions online, and we will.
Thank you very much. It's absolutely a pleasure for me to be in a wonderful, beautiful, pristine country, which is so wealthy with water and natural beauty and sunlight and all these wonderful things, and hydro systems. If you guys can't go green, nobody will go green. But let's get going. Now, this is a chapter from my book, The Practical Guide to Outdoor High Voltage Insulators, and I've decided to make it available to you all at no cost. And it will be sent out to all the attendees, and please feel free to use it. It's a practical guide. It's not a theoretical book. It's a book for utility people. Utility people can use it and help them to select the insulation, do the maintenance, inspections, failure modes, and all these wonderful things on insulators. Also looking at techniques on how to upgrade your insulation and so on. Now, this is a chapter from the book, and it's insulator selection and specification. And I'm just going to start off by introducing you to, let me just get myself here, there you are, and introduce you to the item which is most probably the backbone of our network, and that is an insulator, a high voltage insulator. Now, the high voltage insulator, right, needs to support the conductor mechanically, and it needs to insulate the high voltage from earth potential. Now, if that insulator fails, the line is down, or the line is short-circuited to ground, and we have a flashover and the line is taken out of service, which means loss to our customers. So the high voltage insulator is actually the backbone of our network. You agree? The backbone. And that backbone is most probably the cheapest device when you're building this whole structure or building this line, whether it's in the substation or whether it's on the actual transmission or distribution or MV line. The insulator is actually the smallest costing component in relation to the conductors and the structures and all those things. Now, how do we select this insulator to give you a good life? You don't want to go out there and not be able to sleep at night because it's going to flash over electrically, or even worse, mechanically fail and be a safety hazard to your population. So you need to be able to select this insulator, but select it optimally so that you can actually say, I want this thing only to flash over 1 in every 20 years, or no, I want it 1 in 50 years. To be quite honest, I had a problem to solve in Eskom, which I'm going to show you, where they actually wanted it to flash over only 1 in a million years. Now, let's be honest, okay? I don't think the nuclear power station is going to be around in a million years. It's not going to be around in 100 years, okay? But you find sometimes beam counters can actually come up with the most amazing Yeah, let's put it design philosophies. Okay. Now let's take a look at this insulator. And if you want to design this insulator, now you'll see that I've got here the different chapters, okay, which is associated with the different things we're going to discuss here, okay. So you'll see, for instance, when we talk about the type of insulator, you can go and read about that in chapter 2 and 6. Or the length of the insulator, you can go and read in chapter 3. Or the material of the insulator, you can go and look at chapter 2 and 5. The profile of the insulator, yeah, and so on. Okay. Now let's start looking at how do we design this insulator. There's the insulator in the center. That is where the hub, that is where everything turns around, is the insulator. Okay. So we need the overhead line characteristics. So that's we're working on a power line, okay? And when we look at this overhead line characteristics, we're going to have a system voltage at which this line is going to be operating. I mean, we have to choose a system voltage because we want to transfer the energy from point A to point B, okay? We want to choose a certain voltage which we can optimally transfer this energy across this line. So we're going to choose a voltage. 220 kV, 66 kV, and so on, and we're going to choose a voltage. Are we going to change that voltage? Okay, because that is being selected optimally to get maximum energy transfer. So once that system voltage is fixed, you need to use that to be able to do the design. You agree? Now, that system voltage, when you choose that system voltage, it's going to influence the length of the insulator. The higher the system voltage, the longer the insulator must be. The lower the system voltage, the shorter insulator must be. So it's going to start determining the length. And the system voltage is going to tell you what is the electrical properties which you expect from this insulator. Either from a lightning impulse perspective, from a switching impulse perspective, from an AC wet and dry flashover perspective. It's going to give you the rules for the electrical properties which you need for this high voltage insulator. So you see, system voltage already tells you length. You're going to need a dry arcing distance, a connecting length, an insulation length, a creepage distance. Oh my goodness, look at the faces. So now they're saying, now what is dry arcing distance? What is creepage distance? What is that? That's why I'm giving you the book at no cost, okay? I cannot give you the full 3-day course in 1 hour, but I can empower you with some thoughts, okay? Now when we go, now once we got the system voltage and we got the length of the insulator, okay? Now you're gonna say, right, the structure. What type of structure do I want? Monopole, okay? With horizontal line posts, or stayed, okay, supported, or are we going to horizontal with IVI strings, you know? So your structure type is going to determine also the length of the insulator. The structure type, okay, is going to also determine the type of insulator. Is it a long rod insulator? Is it a line post? Is it, and if you're coming down to MV, is it pin types or is it post types or is it glass cap and pin discs? Okay, so the type of insulator is going to be determined by the structure type. Then also, obviously, the structure is going to influence your mechanical strength. What mechanical strength do you require from this insulator? Okay, when you're looking at a horizontal line post, your mechanical specs is different than from a strain or suspension insulator. Are you guys all there? You look so quiet and so focused. I love it. Okay, so you can see that your overhead line characteristics very much looks at the system voltage, structure type, and it's the mechanical, the type of insulator, the length of insulator, and electrical properties. But now this is not operating in a pristine environment. It's not in the lab. It's out there. Now out there for you, it's actually not so bad as out there for Saudi Arabia or on our west coast or in Australia or in other places. So you need to understand your environment. Once you understand your environment, okay, and the effects your environment is going to have on your insulation, then you can now start optimally selecting your insulator and designing your insulator. So now let's take a look. Lightning. Well, there's classes of insulator, a class A insulator and a class B insulator. In a class A insulator, and you've got a high lightning area, it punctures through the center, and the insulator becomes a problem. I was driving around here in I nearly said Australia, New Zealand. I didn't want to insult you again. Okay? And there I see you've got a lot of pin-type insulators. Now, if you've got a country with a lot of pin-type insulators, okay, I'm saying to myself, these guys, they don't have a lightning problem. Because if this has been running for decades with all these pin types, and they're still happy with all these pin-type insulators, they can't have a bigger lighting area. Then I drive around, and I see you've got tower structures without shield wires. I said, what? That is amazing. The only reason why they could do that is because their rolling spheres are so small that the actual overhead shield wires are not giving much protection for them, so they're going to get a direct conductor strike in any case, so they don't need the shield wires. So they must have very low lightning levels of current, but also most probably a very low lightning intensity structure. Then the electrical properties, again, obviously, is also determined by lightning. So that electrical property is going to say, I want a BIL of this. Now you need to think, at low voltages, below 245 kV, you're normally looking at lighting as being your issue. When you go above that, you start looking at switching impulses as being your issue. So you need to try and look at the electrical properties of what you determine from this insulator. Also, you'll do arc resistance tests, where you do a power arc test across the insulator surface to take a look at where the insulator can withstand different electrical aspects of it. So vandalism and vandalizing is not uncommon. We get guys that actually steal the structures out of the tower and sell it until the tower drops. We've got guys building their house inside the tower. So we've got interesting challenges when it comes to keeping things up. Wind and ice loading, you guys have got wind. In Cape Town, we have wind so strong when you open up your mouth, you lose your piles. I mean, it's tremendously strong winds, okay? Here in Wellington, I felt so at home. It's a windy city, you know. You can stand up against the wind and you can lean against it. Cool, you know. And if you can think about your wind loading, I can see that a lot of your conductors, on your insulators, you've got weights which you weigh down so that you don't get the conductor lifting and swinging too much. Cool idea. And then obviously, believe it or not, in Africa we got ice and snow loading. And so that all will influence your mechanical strength. The wind will influence your mechanical strength, and the ice loading. I mean, there's in Sweden, you can get up to 1 meter diameter ice on a conductor. Can you imagine the weight? Okay. I don't know if you guys got it. And then lastly, but not least, is pollution. And you need to understand the type of pollution in your environment. Is the pre-deposit type of pollution, which is brought in by the wind and deposited onto the insulator surface, and then wetted, critically wetted, either by dew or light rain or so on, and then that forms electrolyte, and then whoop, there it goes. Or is it an instantaneous type of event where you get a salt fog moving in, suddenly insulator is beautifully clean, and then boom, now we got two types. It's defined in IC. I guess who helped define it? Ta-da, okay, put my little flag up, say South Africa helped, you know, cool. And so pollution affects the creepage distance. The creepage distance is the distance from the live end all along the insulator surface, shortest distance on the surface to Earth. So they talk about the creepage distance. Okay? And then the profile of the insulator is what the sheds look like. Do they have a under rib? Or do they have a flat, open aerodynamic profile? Aerodynamic, pollution comes over, and all these little particles are hard to get stuck. Under ribs, deep under ribs, here comes a pollution particle, and then it goes into an eddy, and the eddy spins it in underneath into the rib, and it sits there and builds up and builds up and builds up and builds up and builds up. Can the rain get to it? Is it washing? Oh. So if you've got a high particulate loading, is that a good idea? Do you guys think with your volcanoes, with your volcanic ash, under the profiles is a good idea? I wonder. Read the book, you know? Okay, and so then also what happens is, from a pollution perspective, the type of material. Is it a hydrophilic material, where that when you got the pollution on it, and the pollution basically is deposited and so on, and you wet it, it forms the film, and it forms a conducting film, or the pollution deposits on it, and it turns into a hydrophobic surface because low molecular weight silicons migrate to the surface, encapsulate the pollution particles, make all these little methyl little fingers stand out, and they are creating like a duck's back hydrophobic surface. So now it can't dissolve and form an electrolyte. It can't form an electrolyte. Well, where's the currents? You got it. Remember, this whole lot boils down to a very simple formula. And this formula comes from a very amazing man, a man by the name of Ohm. You know, they say they got this relaxing type of stuff where you go, Ohm. You saw Smokey and the Bandit? You know, we go beep, 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 Ohm. You know. Now, Ohm, he actually came up with this whole little formula of R equals V over I equals V over R. Now imagine in your mind, now I can't write this stuff down, so you're going to use your imagination. So in your imagination, see the following, right? Da-da-da-da. The current is equal to the voltage divided by the resistance. Can you do anything about the voltage? No. Can you do anything about the resistance? Yes. Now, what is R? R is equal to, come along, rho L over A. Right, cool. Now you see it in your mind. R equals rho L over A. What is L? Length. And that's your creepage distance. Cool. So higher the creepage, the higher R, the lower I. You got it? Cool. Now, the thickness of the pollution layer. The thicker the pollution layer, the larger the area available for current flow. So A becomes bigger. If A becomes bigger, what becomes with R? Smaller. R becomes smaller. What happens to I? I goes up. What do you want? I as small as possible. So you wash, you clean, you get rid of the thickness, you reduce the area available for current flow. Cool. So L, increase creepage, and rho, A, you reduce. Now when hydrophobicity transfer takes place, it goes into the material, the pollution, okay? And what happens to A? It becomes smaller, 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 smaller until it nearly disappears. And that's why current goes down. And rho is the resistivity of the pollution layer. As it migrates into the pollution layer, what happens to rho? It becomes bigger, 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 bigger rho, bigger, bigger R, smaller, smaller I. Insulated pollution, explained, done. Rho L over A. I can solve any in-service problem you've got with pollution with R equals rho L over A. And that's it. So simple as that. Now, here's a table. And this table is in the book. And you will find now, yeah, you got a disc insulator, can either be from glass or porcelain, okay? And the pin insulator is normally glass, porcelain, or a resin, like epoxy resin. Folks, cycloaliphatic as a material, the material cycloaliphatic has got an inborn problem. It's got in it an ester, which has got a double bonded oxygen. It's prone to hydrolysis. So all your cycloaliphatic will chalk because of those little double bonded oxygens, okay? It will chalk, it will go white. Put your hand over it, it's like PVA paint. That reduces its wet flashover voltage by about 20%, okay? You will find that the material, once it's subjected to high humidity and localized arcing, the material itself, okay, will break down quite readily, and it will be due to hydrolysis. So there's an inherent problem. It's not to say you can't use it. But you will use, for instance, cycloaliphatic at 38 millimeters per kV, where you would use the porcelain, at 31. Why? Because the cyclo now The surface changes, but now the surface does not interact with the pollution layer. The pollution layer comes into the surface. What happens to the area? Becomes bigger. And as the area becomes bigger, what happens to R? And what happens to I? I rest my case. Right, now we go on. Long rods can be made from porcelain and resin and ethylene. EPRs is the EPR rubbers, which is actually more a EPDM, ethylene propylene diene monomers. Okay, they've got a tertiary carbon atom, very prone to UV. The UV will split the tertiary carbon atom, one shot, boom, and the chain breaks. And as it breaks, so it will break, and as it breaks, it cracks. And as the material cracks open, you find that what happens now to the pollution? It moves into the crack. Right, so now, if you take a look, with EPDM, okay, the surface cracks open, what happens to the pollution? Into the cracks. What happens to the area? Ta-da, goes big. What happens to R? Down, what happens to I? Up. See, rho L over A. And then the other materials which you can get for the long rods is silicon rubber. What happens now to the area? It becomes smaller because it's not dissolvable. So as it migrates up, it becomes less and less area, okay? And the resistivity of the whole thing becomes higher and higher. That's why silicon works so well. But you need to have the transfer. Even though the surface is hydrophilic, inside there's phobic stuff that's happening. And so you go onto the station post and apparatus and so on. You see in this table for the different voltage levels, and now you will see for different types of conditions, whether you got pollution classes 1 and 2, that's light to medium, pollution classes 3 to 4, that's heavy to very heavy, whether these things are recommended, not recommended, applicable or not applicable. So that table, you can go and work around and it will help you to select. Okay. Now you need to go and take a look at the electrical side. And so you're going to have to now look physically at the length and the creepage and the end fittings and so on. So yeah, you will go and select your values for the different system voltages here. You will have your power frequency, your lightning, and your impulse. You see the impulse is only here. They've got it here from 300, okay? And on your mechanical side, you will see your tensile strength, your cantilever strengths, and this is for your fittings and so on. I'm not going to go into this too much because I've got a lot to get through with you. In the back of the book, there's an insulator selection chart. And there you will go, and you will, for instance, go and take a look at your system highest voltage. Okay, you'll look at the mechanical strength you want, and you look at the environment. So yeah, you go through the environment selection side. Yeah, you go through the mechanical selection side, and yeah, the electrical selection side, and this guides you through how to do your selection. Now, that is a whole hour's discussion on its own if I go into detail. So I want to get to the practical example. I want to do all this stuff pretty quickly. Okay, so we can get to the practical. Now, yeah, if you need to go and decide on writing an insulator specification, that's also a course on its own, to be quite honest. I'm just taking a swig of water here. Okay, so yeah. You will see that if you go take a look at the insulator's characteristics and influenced by the book reference, where you can go and find it in the book, and then what IEC test you must specify, the value or the test, and here's everything is there. So in here, you'll see that if you're setting up an insulator spec, that is what is the minimum requirements for you to set up that spec. Very handy for industry. Very handy for industry. So, let's go on. What's available? There's quite a few books. Old Looms' book was always like the father, the beginning guy, was obviously British, you know. So Looms set up that book based on test station work and so on. And then we found that we got Ravi's book here, Professor Ravi Gura from the Arizona State University, and Well, there's another character down below. I can't read his name, it's too far down. This is the Insulator Punk's book, old Frank Schmook. I call him old Schmookie, and he used to have a haircut that stood like a punk, you know, so we called him old the Insulator Punk. we're all friends. I mean, we all work together. We're all in the same IEC and C-grade work groups and so on. This is EPRI's book. And they've also now got another book which is brought out, very glass-orientated, but good book, but very expensive. Now, this is the ice and pollution one, and this is the one I've given you at no cost. So you guys are welcome to go and enjoy that book. But this is the information that's out there which you can use, okay? Now, the guides. Now, the old IEC 60815 was the original guide. Was written in the 80s, okay, and that's it. And that was then rewritten now, and there's now 4 guides. The old guide was set up and did its job, and the new guides are so confusing the majority of people can't read them. And that's why I'm going to try and help you a little bit on that. Now, in the old guide, you would either choose your area light, medium, heavy, very heavy, and then you will go and you say, if it's light, you use 16 millimeters per kV, medium 20, and these are all in your head. It's a very heavy area, 31 millimeters per kV, medium 20 millimeters per kV. And the supplier, you'll spec that, and that's about it, okay? And then you say, oh yes, and by the way, it needs to comply to the profile of IEC 60815. Okay, now what is that millimeters per kV? That's that creepage distance you measured, and you divide it by U max phase to phase. Okay, now why they do that? Okay, because that's not the voltage over the insulator. It can be the worst case scenario in some very unique situation that it would be the voltage, but on the normal, so it was, you know, and then the railway guys come along, and now or the DC guys come along, and oh my goodness, now we're really confused what's over the insulator. So now what they did is they changed that now to unified specific creepage distance, where it is actually the voltage over the insulator, not phase to phase, 0, and so on. Okay, so now this is the different profiles, and you can see here, this is from the old 60815. So you would say to the supplier, I've got a heavy environment, I want 25 millimeters per kV, and I would like an open aerodynamic profile with the intershed spacing to projection ratio of 1. That's my spec. And everybody's happy, and out comes the insulator, and there you're done. And then you would also say, I don't want a drip lip, because that's a drip lip. That was an idea for porcelain at its time. And here you can see the alternating shed profiles, and here you can see the underrips. I don't want any underrips because they're going to be collecting pollution. So that's how you can spec, okay? And this was nice and simple, and everybody was hunky-dory, and they did it. And most of the utilities still do it, because then this monster came along. The IEC 60815 latest update. 4 documents. The first one is with definitions, and the second one is for ceramics, the third one is for polymers on AC, and then comes the monster number 4 for DC. Okay, now you must remember there was a lot of C-grade work groups that went prior to this, where the guys sat for over 10 years to work out and get everybody's data and information together and set it up. Now, in a nutshell, you basically go and you measure. He who measures knows. So now you need to go and measure your environment, determine your pollution severity levels, and from there determine what is your actual conditions. And then you go and you select a reference unified specific creepage distance. And that you go, and now you go down into the document, and now you go and apply correction factors, or you decide on what to do. And now you'll find those correction factors very much manufacturer driven. So they don't want it to be an exact value. So they will say to you, that will have a major influence. And you've got this big buffer. This will have a minor influence, and this will have no influence. So now what happens is now you're confused. So they say, okay, what do I do? Okay, as utility, you're fairly confused. So the manufacturer decides for you. That's what he wants. Because you as a utility is not sitting in IC and C-grade. You're not representing your country there. You're not fighting for what you want. Because remember, you as a utility, you're the boss. The supplier must supply you. The labs must test for them. You should be setting what is required, not them. But you've empowered them by not sending your people to attend these things, to go and represent you, to represent your country and what your country is about. Try and get representation on IEC and C grade, so that you can say what is required from your perspective, from a utilities perspective. And there's very few of us utilities guys. I'm one of two guys on that whole IEC work group on writing these specs. And we have hell to get it right. Then once you've got that, you've done all your corrections and so on, then you will now determine your insulator. And you can see here, it's basically encouraging you to measure, and once you understand your climate and your environment, and you've measured your climate and environment, and you do your selection, and your referencing, and so on, and you're going to basically have to get used to the story of specific creepage distance and unified specific creepage distance, which is now UMAX phase. Okay, we've got that. And yeah, you can see now, we were used to 16, 20, 25, 31, and now you're going to be specifying 27.8 or maybe 28. Now, the supplier comes to you and he delivers the product, and the product's wrong. Because he wasn't certain, is it now specific creepage distance or unified specific creepage distance or whatever, okay? Don't specify specific creepage distance like 16 millimeters per kV or unified specific creepage distance of 28. Specify the actual creepage distance, because then you can't go wrong. So in your specs, rather use your creepage distance in your spec, okay? So that would help you on that. And then, yeah, you can see now you measured your non-soluble deposits and your soluble deposits, which is now your equivalent salt deposit density values. And from here, you can determine what's the pollution severity levels in your area. If it's a very light area, very light, you need 22. And if it's B, which is now light, you need 28. And now you see these values are far higher than what we were used to because of the square root of 3. Square root of 3, the little bugger came around and bite you right on the toe, because that's where you make your mistakes, okay? Equivalent salt deposit density, that is how much salt, okay, in milligrams per square meter do you need on the surface of the insulator to get the same conductivity of the pollution that's there. See, then you take that, dissolve it all, put it through a filter, how much non-soluble stuff per square centimeters there. And then you can get the two values. That's a whole process. That's a day's course, okay? We can use dust gauges to get it, directional dust gauges, where we then measure the pollution from different directions, capture it into the dust gauge, and then from there we can determine our environmental pollution levels. Very cheap. You're looking at about under $300 for a set. When you put on top of that a surface conductivity little device, which is energized every 10 minutes at 600 volts, you measure the current, you get the surface conductivity, you can get at 10-minute intervals your pollution severity levels. There you're looking at about $2,700 for a device. Now, what you need to do is, okay, there you can now see the different, they also still got the table and so on to do it. But what you can do is that we do environmental impact studies, all right? Who pays for it? We do. Costs us an arm and a leg. What does it do? They tell us what we need to do to protect the environment. We need to ask them to tell us what the environment's going to do to us. So that means they need to tell us what's the presence of birds, what's the winds. So we need to specify in our environmental impact study up front. We would like pollution severity levels, we would like the impact of birds, and so on. And then you use that and you capitalize on your environmental impact study. Get them, because they're making a lot of bucks out of us. And for those tests, $300 for a little device to help you to do it is to walk in the park, and to do it is very easy. Now, the new 60815 has got 3 approaches. The one approach is you use past experience, or you measure and test, or you measure and design. And most people don't even measure, they just design. This will give you a pretty poor end result, and you will either over or under insulate. You're going to live with a lot of problems. Yeah, you measure your environment and then you go and test in the lab. Yeah, you use outdoor test stations or line experience, best approach. I use a combination of these 2 approaches here. Now, what we do is that in 60815, they've got a statistical technique for optimum selecting. It's very similar to lightning. So what we do is on this side here, we got the actual environmental stress. So we will take our pollution measurements, and then we will do this log normal distribution on that environmental pollution. Then on this side here, we have our product which we want to find out the performance of, and we will determine, in the laboratory, we will determine its pollution performance curve. Then what you will do is you multiply the two with one another, and you get a risk. Same as with lightning. But what this thing boils down to is that you measure your environment and you get the stats. You go to the lab, you do a pollution performance curve, and you get your stats. You take the two curves, and then you work out your risk. Now, your risk is the vector product of the two curves, so you multiply two curves together. It's not the vector, it's just to multiply two curves together, and then you integral, you get the area. And once you got that, that's for one insulator. Now you would then correct for number of insulators and number of critical events. And there you go. Let's see how it works. It's going to take that's a book we're busy writing. I don't know whether we're ever going to finish that book because it changes so quickly. I've got a little bit of more time, eh? Is it okay? Cool. Then I can show you this. Okay. Now, we've got a nuclear power station. And we want to expand this nuclear power station and build 2 new extra units. We've already expanded the nuclear power station's lifespan to 60 years. It's the cheapest electricity in South Africa. And, it's the cheapest electricity in South Africa, most reliable and cleanest. Yeah, believe it or not. A nuclear power station has got 3 times less radiation than from a coal-fired power station. Get over it and get used to it. All the energy on Earth comes from nuclear. Comes from the sun, which is nuclear. The rest is all derivatives of nuclear, so also get over that. So when you sit with a scenario where people are whooping and harping about we shouldn't be using nuclear, you tell them, well, you need another planet, okay? Because unfortunately, you have got all your energy coming from nuclear, and that's it. It's just how you use it, but I won't go in there. Now we need to build a new substation there, obviously, and this substation, we need to do the design, and we want this substation's insulation optimally selected, okay? And then the guys came up with a stupid, ridiculous figure of how many years between flashovers. So here I am, and I need to choose a methodology. So I went and I said I'll follow approach 2, where I measure the pollution in the area and the climate. I do a test in the lab, I come back, and now I calculate risks and try and select my insulation in such a way that I can reduce my risks to 1 flashover in gazonks years, okay. Then in doing that, I need to determine the type A pre-deposit pollution and type B instantaneous pollution and the severity levels and climatic conditions for that area. I need to go and determine laboratory pollution performance curves. And then I need to come back and use the stats. Yeah, IEC 60815 is based on this. But guess what? In the whole 4 documents, there's 1 page, which is that little page I showed you, how to do it. And it doesn't tell you how to do it. It basically just tells you that's available. So here you sit with these 4 documents, which actually say that you must start doing something, and they don't tell you how. Now let's take a look. Here's our nuclear power station, and there's the intake, and there's the outlet, and so in comes the water, goes through and does the cooling part on the turbines and comes out. By the way, that is like a radiator system. The turbine section is totally isolated from the seawater, so that's another barrier in the whole nuclear arrangement. Here I've got my test station, which you saw there on the photo, Kubrick insulated test station. Now remember, if something has got a dust gauge index of larger than 350 microsiemens per centimeter, it's very heavy, okay? Look here, my average, 2,522, some of the highest in the world. It is actually seen as the highest in the world, where people have measured and know. There might be higher, But we haven't measured and known there. Okay, sorry about that, folks. My hand was a little bit too descriptive here towards the mic. So if your ears are still all right, that's I'm very pleased. Okay. So now that you can see is on the sea, 50 meters from the sea. Now take a look here when we go to Janse Gat, okay? That is 100 meters from the sea. There's a reason for that, but I won't tell you the reason for it. Now there's 100 meters from the sea, okay? But it's on the upwind side, after the power station, you see. Still very heavy, but it's like 4 times lower, see? And then here we measure at the Golden Mule. Now the Golden Mole is this very unique mole which just lives there, you know, according to the environmental guys. So all we did is just put a few cobras there. Now the Golden Mole is so we're planning on wanting to build, most probably looking at this as a substation, okay? Now you can see here where we got Sea View, which is, I mean, Robbie Watson, my sidekick, comes up with these amazing names. But okay, Sea View here is 400 meters away, and we've got 137. 137, we're coming here to medium. My goodness, extreme down to medium. And 2 kilometers inland, 2.5 kilometers inland, light. In the same area. And now if you had to work on this results here, what would you have done? Extreme, okay? And look here, Dana substation was a sub that was built when the nuclear power station was built. It was the supply. It's here in the heavy, okay? And very heavy, but it's not so extreme as here. So now we got an idea of the pre-deposit pollution levels. Now, we have instantaneous pollution events in the Cape. It happens about every 6 years where we get these intense salt fogs occurring, and then it takes out the network. And it only started after 94. It is because the ANC has been migrating a lot of guys down to the Cape to win the Cape politically and have ANC power in the Cape, so now they've got a lot of squatter camps, a lot of people living as squatters where we previously had pristine air. Now we're getting a lot of smog and a lot of fire smoke and a lot of veld fires because the guys are starting veld fires, and so now our particulate loading in the air is far higher than it ever was before. Now, what do you need for a fog? You need a particle. If it's a clean particle, you get a clean fog. If you've got a salt particle, you've got a salt fog. If you've got an industrial particle, you've got an industrial fog, because the moisture condenses around the particle to form the fog particle. Ah, cool, eh? So now what happens now is we got this extra particles now. And now the problem is that we get the salts coming in and they combine. And now we got what we call instantaneous pollution events which are occurring. You can have beautifully clean, pristine insulators, and then in an hour, and then when you finish, what's left on the insulator is nothing, because it was a sudden electrolyte boom and there's no ESDD really left. So what we did is that we went and we took the results from a 132 kV breaker. We got the creepage of nearly 33, so 32.4 millimeters per kV. And we know that it flashed over during our events. So we could re-engineer backwards, making use of Ohm's law and some other little formulas. And we could calculate that it should have had a 0.4 milligrams per centimeter squared. That's very high. So now we got an idea of what happens during such an event. Now, we need to know how many days in a year do we get fogs. So we got a map of South Africa, of the Cape, which shows us that we can look at about even more than 40 fog days per year. So we can think of 40 critical wettings per year if we assume it's just a clean fog. And then what we do is we say that at least once a year, not every 6 years, but let's say work it once a year, we've got this extreme conductive fog. Boom. So we set the scene. Now, we went to the lab, and we took bare porcelain and 2 different RTV coating porcelains, and we took a hollow core and a long rod, and we did the pollution performance curve tests at Street in the lab. There we got the A and alpha values for the curves, and I can't explain that to you now because it's just we don't have the time, but I can tell you that for hydrophobic and hydrophilic surfaces, we got the values, and we went and we said, right, now we got the tool. We got The environment defined. We've got the curves of the different products. Okay, let's go and test to see if this tool works. Does the stats work? EU measures with calibrated instruments, knows. Okay, so what we do is we take 60 porcelain station posts in Dana Sub. We know their performance, we know their creepage distance, okay, and we know what happened to them during and after the event, the big instantaneous pollution event. Oops, this poor mic and the poor guy's ears. I must get my descriptions a little bit smaller. Prior to this upgrade of the substation, we had flashovers occurring on an annual basis. We had flashovers in that sub every year. Then we put RTB coating on, and to date, actually now to date, which is some years even later, we haven't had a single flashover. So now we got a good in-service performance. Flashes over every year, a few times. If we don't have the coating on, and if we've got an RTB silicon rubber coating on, we only have no flashovers. Cool, so we got performance. We're also measuring inside that sub the actual pre-deposit pollution with ESDD and NSDD and dust gauges, and then we also now know what has happened with the dust gauges and so on, so we got all the data. So we go and let's go look at the stats. So if we use just the bare porcelain, it will flash over at least 2.5 times per year. That's our experience. It's flashing over quite a few times per year. Quite a few times, 2 to 3 times, 2.5. Hey, that's cool. That's not bad. Okay. Since we put on the coating, we haven't had a single flashover up to now, and it's going to be a little long time for us to wait for 2,000 years. But okay, that is now, remember, for pre-deposit type of pollution. Pre-deposit type of pollution. So if we've got a pre-deposit type of pollution event, with the pre-deposit pollution, we will have 2.5 times per year for the bare porcelain, and we're looking at the coating on flash. Now, we need to say, what if this thing is exposed to that severe pollution event? Well, the porcelain will flash over every time. But the coating, no problem. Our tool works. So we're happy. Tool is working. Now we go and take a look at the substations we want to build. We want a 400 kV sub, 132 kV sub, that breaker and a half-story designs and all those issues. And now how many insulators are we going to have there? Because remember, statistically, we've got 1 insulator, okay, then your risk of flashover is far lower than having 100 insulators. So now we need to find out how many insulators do we have so we can calculate our risk. Cool, there we got. So we're going to need so many coated ones, so many alcohol ones, and so many silicon for the 132 one that we do it. And then we go and we say, okay, let's just get a few things here. Now, if I'm looking at 132 and I want 20 millimeters per kV or 25 millimeters per kV or 31, what creepage do I need? You know what I mean? And then if I go here for specific creepage of those levels, and I want for 132, so what type of creepage do I need? And then you'll find it's quite interesting. With the old system, the difference between 16 and 20 is 4. The difference between 20 and 25 is 5. The difference between 25 and 31 is 6. So the next one must be 7. So that's 38. And if you want to go down from 16, it must be 13. Yeah, cool. So you see these old guys, they did their thing, okay? And here, I've got the conclusion slide, the last slide I'm sharing with you today, okay? And this is really showing you how strong and how effective you can use this tool. You've used your environmental impact study to get your data from the field. You've drawn up your stats for your pollution. You got your data from the lab, which you spec'd. You're taking the two, and now you're going and you want to now do the selection. You got all these values, eh? So this is now for the 132 kV sub. This is for the 400 kV sub. Right, let's start off. Okay, I specify 31 millimeters per kV. So for a type A pollution, for the porcelain, I'll be getting a flashover every 0.1, mean time between flashovers of 0.1 year. So take 0.1 times 12, my goodness, you know, we're getting flashovers galore, okay? Now if we go and take a look for type B, which is instantaneous pollution, I'll be getting just less than 2 years between it will nearly be about 1 flashover every year if it occurs, okay? Now we go and put a coating on that porcelain. And I use this coating from this supplier. I will be getting 18 years between flashovers if I use that coating on the 31 millimeters per kV for type A, and about 19 years for type B. So, hey, cool. I'm looking at about 18, 19 years. That is actually not bad. If you got a flashover only every 18, 19 years on that sub insulation, because it's now RTB coated porcelain, cool. Oh, but coating won't last 18 years. We've got more than 20 years on coating in severe environments. But there's good coatings and there's poor coatings. Because the other manufacturer's coating down here, you will be getting a flashover every 0.3 years, and you will be getting a flashover every 2 years. So, my goodness. So you specify out there, I would like a RTV coating. It must be hydrophobic. And both of these guys tend to come back. And now how do you know which one to choose, and how do you know which one is performing better than the other? Get your pollution performance curves, use it, and make a decision. See the power of the tool, power of the process. Now we go on, and we say if we use hollow cores, we'll get more than 300 years for the pre-deposit and 29 years for the instantaneous, and so on and so on. So we say, you know, and yet on the 400s, it's even better. But you say 31 millimeters per kV, nah, maybe that's not a good idea. 31 millimeters per kV is not bad, but I'll definitely not use this coating, I'll use this coating, and it's actually not too bad. But if I go for 38 millimeters per kV, both coatings will do okay. You're not overstressing the second coating. Look here, the values. Okay. So 38 millimeters per kV. You would find that would give very good performance for that substation. So if that is what you're going to use in your design, you can now go and sleep at night. And now if we go back to here, is that if we want at 132, we want 38 millimeters per kV, we need that creepage distance, okay? So now where can I get equipment with that creepage distance, okay? So now I need to go and take a look here and say, okay, that's 555. If I build it at 275, you know what I mean? You see where we're going? This is where this table comes in. So you might spec the thing for 500 kV, so you could get 38 at 400 and so on, and so you start playing around. You see what I mean? And this here is how you should be using IEC 60815. So the concept would be to use 60815 correctly. Measure your environment, get your data. Look at your climate, get your data. Go and get a reference or a candidate and get candidate insulators. Have them evaluated, get their pollution performance curves. Take the two, go in, do the stats. From there, what voltage? Okay. What line performance do you expect? And by the way, bring in life cycle costing. Because by bringing in, now you need to convince beam counters to go for something which is maybe a little bit more expensive. But you need to look at life cycle costing to show them that the selection which you are actually proposing is going to long-term be the most cost-effective. And don't take and forget the whole scenario of getting rid of insulators at the end. Because to get rid of insulators at the end is a cost which a lot of people tend to ignore. And there, between the different materials, getting rid of these things can be quite costly. So your initial cost is not the big thing. How many times are you going to lose your customer? How many times do you have to re-insulate? And by the way, you're going to find suppliers of manufacturers of products coming to you and saying to you that the lifespan of a composite insulator is only 15 years, based on the American studies. The American studies was done where the insulators at 220 kV was not fitted with corona rings. So those insulators were overstressed, and those insulators are failing now. And there's major replacement, and now they're going to go back or actually move towards glass discs, which suits certain suppliers. And those suppliers are the guys moving around telling you, listen here, you need to go for glass cap and pin discs or coated. And there's nothing wrong with the glass cap and pin disc. You guys have got some good experience with glass cap and pin disc, I'm certain. And also going for an RTV coated glass cap and pin disc is also a good idea. It's not a bad idea, okay? But the thing is this, is that it doesn't mean you have to go and re-insulate and get rid of all your composites, because you got corona rings on and you got them correctly installed, and you now need to just monitor and see whether they are okay or not. So never believe a manufacturer or a supplier. Always make certain you double check and see there is always some agenda which goes along with it. But every product has got its usage. You need to just understand the material. You need to understand the insulator you're working with. And there's pros and cons in all of them. You can use a EPDM, for instance. You just compensate for certain aspects, which means the area is going to increase. So you need to go for a longer creepage. So you need to increase L. You see again, rho L over A. And I think with that, I need to open up for questions, because otherwise I'm going to keep you here till breakfast. Is there any questions from you guys? Yes, sir.
You mentioned the insulator made for around 1 million year failure. What was that for?
That was for that substation. I convinced them it's not necessary for 1 million years. Yeah. But that's bean counters. Yeah. Right, sir?
These RTV coatings, how long do they last?
Well, we've got more than 20-year experience with coatings locally. I've evaluated most of them in relation to one another. There's very poor coatings, terrible ones. I've got ones that have flashed over 4 times in 1 year in my test station. I've got other ones that haven't flashed over to date. So, yes, they work, and no, they don't work. It depends on the coating. Now, I can tell you, which is quite interesting, is there's an optimum thickness for the coating as well. Because when you start looking at how this coating works, you got your porcelain as your base, or your glass as your base. That's a heat sink. The porcelain is a heat sink. So now you put a little blanket over the porcelain. So now the sun is shining, and the energy from the sun is transferred through the silicon slowly into the porcelain, and the porcelain is heating. But now the actual coating is covering like a little blanket. Now remember, it took long for it to get in. It's also taking a long time to get out. So your porcelain insulator now is hotter than a composite next to it. So now what happens is, for dew to form on that RTV coated porcelain is more difficult than it is on the normal bare silicon one, because of the fact of this temperature retaining. But also what happens is that you normally have in your coating or in your insulator itself, you've got alumina trihydrate. Alumina trihydrate is actually water molecules which can become available. Aluminium, okay, with OHs, and then when they break off, they become water molecules, and then the arc heat is transferred into the water molecule and explodes, and as it explodes, it shifts the arc, and that's how you get arc resistancy, okay? So now with the coating, you must normally coat between 0.3 and 0.5 millimeters, not much more than that, because once the arc is moving around, the temperature of the arc is now not only transferred and causes the alumina trihydrate to go, but the heat is also transferred into the porcelain and sunk into the porcelain. So it reduces the arc root temperatures. So you find that your erosion or tracking and erosion on the coating becomes far less. Now, mostly on silicon, you don't get tracking, because tracking is a conductive path. So if you want to determine whether it's tracking or erosion, you would take a mega, 2 pins, and then you put it over the area where about a few centimeters in between the area, and then you measure. If it's conductive, it's tracking. If it's not conductive, it's erosion. Normally silicon has got problems because of the composition of it and such a material structure that normally the silicons erode. But I didn't diversify too much, not answering your question. So there is, so what I would do, for instance, here, I will have a little in-service test facility, like in-service test station online. I build them, it's easy. You can use the existing tower, put up 9 insulators in it, which is coated with different coatings from different suppliers, and you evaluate them, and then you must live with the fact that 1 or 2 of them is not going to make it, yes.
Have you considered any fault conditions as well?
That's, pardon?
Any fault conditions in the substation?
Fault conditions? We monitor the leakage currents on products, and then from there I can determine how close they are to flashover, and I can tell you what to do, yes. So we actually can monitor the condition of the insulator, and then from there predict whether it's going to cause a problem. But fault conditions in the sub, when there's been flashovers in the sub and so on, National Control very quickly, we know very quickly about what's happening where in the zoo. Yes?
Yeah.
Hey, all the questions are coming now. Cool, yeah?
So you mentioned that it's not trivial to dispose of certain types of insulators, and there's a cost associated. What types of insulators?
Well, now think about it, the materials. Porcelain. Now, I do flint knapping. I make knives and stuff out of obsidian flint. It's quite an art, and I make spear points and so on. Now, I can't find obsidian flint in South Africa. Guess what I use? Old porcelain, fully vitrified porcelain insulators. And then I normally shatter them off and break it. But now that porcelain, to get rid of it, it's as hard as hell. Are you going to just throw it in a landfill, or are you going to use it? Okay. Glass cap and pin discs, got glass. What I do with the glass, I get the old strings, and I make nice book racks with it. So the other guys take those porcelains and make artwork with it and so on. But listen, if you've got a few million of them lying around, you need to do some serious artwork, So you can use it for landfills and so on, because the actual material itself is inert. It doesn't really react. It's not alive. So the material itself, you can grind it down or bash it up or use it as, maybe make it into material which you can use the glass. You can reuse the glass. The glass you can reuse. But then the metal you can melt down, and so you can get recycling processes. Okay, so now we go into cycloaliphatic, which is a resin. Now you're going to grind that up and make a polymer concrete, or so there's a lot of, and then now you come to the silicons. So now you've got this epoxy resin core with fiber, and you've got the end fittings, and you've got the sheath, and you've got the sheds. But obviously there's not millions of them going around, okay? But so you can see there's costs involved. Whenever you look at these things, there are costs involved getting rid of it. There's another question. Yes, sir.
So I was going to ask whether the application of those silicon could be done sort of retrofitted to an in-service insulator, or is that something that has to be done? Is it a manufacturing process, or is it something you just paint on yourself? Or?
Oh, the rubber. You mean the coating?
Yeah.
No. You can do it yourself. The guys can train you. There's different types of applicators or application techniques, and you can do it very well yourself. Any other questions? Are you letting me off so lightly?
Just one more thing. What makes the hydrophobicity of the silicon over porcelain that makes it so much stronger and resilient towards these events?
Okay, you're going to get me into explaining to you how hydrophobicity transfer works.
Well, like how is it, how is it dramatically that much stronger?
Well, let's think about this. Okay, bare porcelain, pollution layer, nice and thick. Does the pollution layer interact with the porcelain? No, inert. Now, is there any way you can improve that? Well, you'll have to wash it off to get the area as small as possible, okay? But now you wash it off, now it's back again. What could be back in the next hour in the form of an electrolytic layer, which is still philic, and boom. Okay. Now we go, take the bare porcelain, put a coating on it. Now you put a water drop on the coating, runs off. Put another drop on, runs off. My goodness, hydrophobic. Get an instantaneous event. Can it form a film? No. Cool. No flashover. That's how it works. But now you've got pre-deposit stuff coming. Okay. Builds up a thick layer. As it builds up the layer, this layer now interacts with this active silicon down below. Now in the silicon, okay, you find you've got silicon oxide, which forms a strong backbone. You need a lot of energy to break that backbone. Okay? And then on that backbone, there's little hairs sitting. CH3s, methyls, sitting here. Now, as the surface is normal, all these little hairs are sticking out, and when a water drops come, a polar water drop comes along, this polar water drop says, oh my goodness, I can't bond to anything, and so on, it rolls off. Okay. But if you come with a piece of pollution, and here comes this big fat piece of salt, and it goes and lands on there, punk, and the salt now is polar. But it now sits there. And van der Waals forces between the silicon oxide backbone and this piece of salt sitting there now holds it on. And as it's holding it on, all these CH3 said, I don't like this polar thing, and they move away, and all these oxygens, okay, log on and hold the salt particle there. So now it's stuck. But now when you wet it, it forms still. Because there's now a polar thing there that's going to be getting wetted. Now inside the silicon material, there's short little chains, okay, which is silicon oxide, silicon oxide, silicon oxide, silicon oxide, with little CH3 hairs on them, not like this, but they're small like little sea urchins sitting in there, okay. Now they are smaller and they can move. So now what happens is their little CH3 hairs say, we don't want to show towards the pollution, this polar thing here, and the oxygens are drawn out, okay, and they pulled out of the material and they migrate. Low molecular weight silicones. Low molecular weight is there's very little molecules there, so it's a small little chain. It's a low molecular weight chain, and this little chain is this little thing that is now migrating out. And this polar thing here is attracting it, and these oxygens here are attracting to the polar. Out migrates. These low molecular chain silicons migrate to the surface, and they start encapsulating the pollution particle. All around. Now remember, these CH3s don't like a polar thing. So what do? They all go outwards. So now what is around this polar thing in the middle? All these CH3s, these methyls. What are they? Hydrophobic. So there you got a hydrophobic particle now. And that's how low molecular weight silicons migrate to the surface, encapsulating the pollution particle. And that's how they migrate into the actual pollution layer. And as they migrate into the pollution layer, is this bottom part in the layer dissolvable? No. But the area at the top is becoming smaller, smaller, smaller because they're migrating up. So what's happening to the area A? Becoming smaller, smaller, smaller. R goes up, up, up. The resistivity of that whole layer goes up, up, up. R goes up, up, up. I becomes small. Your risk of flashover far lower. You got it? Cool. You've been empowered. What other questions are there? Is that it? Oh my goodness. Now I can go and sleep and then start lecturing tomorrow again. Thank you very much. And I like the fact that I have an audience and a very creative and interactive audience. Thank you. And I've loved to share with you guys. And please feel free. You've got the book now. Read the book. Enjoy the book. I've also written a high voltage book, but I'm not going to share that with you because that's becoming the course. And I will be giving it to you once I present the course. Because I want to empower you with high voltage. And the only way I can do that is to try and get me to come and can give you the fling on it. High voltage is fascinating. It's fantastic. And being a physicist and come from a physics background, you can actually make it alive. And high voltage is very much alive. So thanks for being here. I enjoyed having you here.